Brad Williams, Frugal Finance, discrete cash flows. What the heck is discrete cash flows? Well, hang on, I'll tell you. Imagine you're dealing with money that you either put into an account or take out of it, and you're doing this over time. When we say discrete flows, we mean these transactions happen at a specific point in time, like every month or year rather than constantly. There are different ways to calculate how much your money grows or shrinks over time, depending on how often you make these transactions. If you're doing it continuously, like every second or minute, that's called continuous compounding. But for simplicity, let's focus on when you're doing it discretely, like once a year. When you're dealing with discrete flows, there are formulas you can use to figure out things like how much money you'll have in the future based on what you put in now, or how much you should put in now to have a certain amount in the future. These formulas involve some fancy math like E, which represents a special number, and EXP, which means raising that special number to a power. But you don't need to worry about that too much. Just remember, if you're putting money into an account over time, there's a formula to figure out how much it will grow. If you want to figure out how much money you need to put in now to have a certain amount later, there's a formula for that too. To sum it up, discrete flows basically means dealing with money transaction that happens at specific times. And there are formulas to help you calculate how your money grows or shrinks over time based on these transactions. Let's assume cash flows are individually spaced out over time, then the continuous compounding relations for the uniform gradient and geometric series can be used. Substituting EXP R of n for 1 plus I of n, EXP R minus 1 for I, and EXP R of m for 1 plus n in the remaining discrete compounding formula yields the continuous compounding interest factor summarized in 2.4. My recommendation here is go back to the very first example I pointed out. Here is the same formulas, here is the name, but I didn't explain what the use is. In the very first example, I broke this down. Here are your continuous compounding formulas, and here is the discrete formula. Here's the discrete cash flow. So depending on what you're looking at doing, this other notation, this is aimed at the engineering side. As I mentioned before, this is not my forte. I don't do this, and I don't do this either. I don't discuss this at all. So you're on your own, engineers. You're crunching numbers, doing it in a different style than I do. And there's nothing wrong with that. You may have been taught this, and so that's why I provide this information. Then summary of continuous compounding interest factors for continuous flows. This is just going to be this information up here. And then to illustrate the use of continuous compounding interest factors, suppose $1,000 is deposited each year into an account that pays interest at a rate of 12% compounded continuously. That means it's compounded every day. Determine both the amounts in the account immediately after the 10th deposit and the present value equivalent for 10 deposits. So here, all we're doing is we're taking 1,000 deposited each month for 10 years at 12% continuous compounding. That should be the equivalent of this right here, 10,000, 1,000 each month. So that's the equivalent of EXP 12, and that should be the equivalent of this uniform series present value. In the present value, all we're going to do is reverse this. So here we have this factor. All we're doing now is just determining the factor, because $3.32 wouldn't show the value. So 1,000 deposited for 10 years, and I'll show you how this works here in a second. Here it is right here. But I'm just going to break this down. If in the event your computer system blows up on you, you can do this manually. This is a present value factor. As I mentioned, is old school. When I started doing finance a zillion years ago, in the back of every finance book were compounding tables. That's all this is. I'm showing you the compounding using continuous compounding. Here's the factor. You would use this. This is just simply the present value of 12.75, 10 years minus C52, which is right here. It's $1. Why? Because we're not doing anything. All we did was find the factor. Then 20% effective interest rate compounded daily. We can use the effect function within Excel. If we need to find the nominal rate, I'm a little bit off subject because that's not part of the question, but I just threw it in there anyway. That being said, here is just a map. The map is just the way to do this. If you can't just visualize this thing, an investor invests $1,000 every year for the next 10 years at 12% continuous rate. What is in value? We're going to have 10 periods here. I'm just going to go 1, 2, and then I'm just going to grab this little green box, copy it down, and it just does that automatically. We're going to set this up here, and here's your EXP. Here's the formula. Here's your compounding, continuous compounding. Notice we have EXP, not 1 plus 12 to the power. For simplicity, I should just note this, and this should be 0. We have this factor. Why are you using factors? Purely a tutorial. All you're going to do is you're going to take this EXP1 to the 12th. We're going to grow this thing out. This would be some large number. We're going to divide it by this number. This is just a compounding. And then the 54810 is this factor. And this number here, this factor, would be the present value. The present value of this 18,197. My suggestion here is to look at these formulas that I provided. Go up here and compare them. And then just through practice, you're going to see how this plays out. You may need to go to the very first example, page 1, page 0 of this series, and look to see how this works out. You can also remove the EXP and add 1 plus the factor. You could go 1 plus, what would we use? 12%, 1 plus 0.12, and it'll provide daily compounding so you could visualize it and do the same thing here. They're intimidating looking formulas, but you're just going to break them down. If we're looking at present value, just think of what we're trying to do. We're trying to discount this number back to this $1,000 over a 10-year period. That's what it's worth today, 5481. What does that mean? That means if you were to put $5,481 into a bank account today, earning 12% continuous rate, 10 years, it should be worth $18,197. You receive an annual bonus, and the size of the bonus increases each year at a rate of 10% compounded continuously. The initial deposit is $500. Initial deposit right here. How much will you have after the 10th year? In this case, ACE of 1 equals 500, R is 8%, C equals 10, and N equals 10. Similar to what we've been doing before. So here's our factor, and I mapped this out so you can visualize it. Here's the compounding, here's the interest rate, here's our value, and this is how it grows. You're gonna have 540, and it's gonna grow $52, $33, $33.47. With continuous compounding, what's going to happen? And that's the power of compounding. That's why we're doing this. You're going to see that this thing grows to $11,785. Keep in mind, we're putting in, and this is 500 initially over a 10-year period. What you're asking is the compounding effect. Without the formulas, you can go, well, there's going to be $5,000 at least in the account. And then rough and tumble, we can go 500 times 1.1, and so here you can just see the effect. We're adding 540 and then 52, and then there's this growth factor. You're adding 500, 500, 500, 500, 5, and then but there's a 10% increase every year. So in the end, it's 11,785. Now you can see how hard this would be without the formulas. You could go 500 times, what is it, 8% or 10%? It says you receive an annual bonus size 10% compounded continuously deposit. After that, it's 10th year. So yeah, 8%. All you're going to do is 5% times 1.08, 540 times, what is it, 10% growth times 1.10. Then you're going to take that number and you're going to multiply it times 0.08. Then you're going to take that number and multiply it times 10%. All you're going to do is just take that. Well, here, I'll show you. No, I was going to show you, but I'm going to allow you to do that on your own if you need to. The logic is pretty simple. In this case, A1 equals 500, R is equal 8%, C is 10%, and N is 10%. So you're going to have this 126. So there's your number, 114, and then 126. 126, EXP is 57. What does this mean? I'm going to let you work through this. So in the end, and this is important, understanding continuous compounding, because we're going to use this time and time again. Lastly, familiarize yourself with this information up here, these formulas. And because we're going to be focusing a lot in terms of the continuous side, here's these formulas, and then just take them apart if you need to. In other words, just come up with a hypothetical and plug and chug. Brad Williams, Frugal Finance. More to come.